Hello guys, and welcome to another calculus video. In this video we're going to be solving this awesome infinite product right here. Um, so as you can see, we're taking the limit as n goes to infinity of e to the negative n times the product from k equals 1 to n of 4k squared over 4k squared minus 1, all raised to the 4k squared minus 1 power. And this is going to be a pretty straightforward problem. All the steps are going to be pretty methodical, and there's not going to be, really any complex methods here, but I think it's a really fun problem with a lot of different nice little tricks. So let's go ahead and jump right into the problem. So we're going to start off. Oh, also I would like to say I got this problem from the Cambridge integration server. We're just going to call this product P. The first thing we want to do is we want to just make it into a product from k equals 1 to infinity, because dealing with limits and products at the same time is usually not too nice. So what I'm going to do is rewrite e to the negative n as the product from k equals 1 to n of 1 over e. And that means we can actually combine these two products, and this should be raised to the 1 minus 4k squared power right here, because what I also did was I flipped 4k squared minus 1. I flipped this over, and then I changed the power again. So this actually becomes 1 minus 1 over 4k squared to the 1 minus 4k squared power. So now what we're going to do is we put this all into one product right here, and then notice we have this 4k squared, and we also have this one that's separate, which is just the 1 power. So we're going to separate this 1 power and the negative 4k squared power into two separate products. And now, since everything is in one product, we can just go ahead and let the upper bound be infinity. So we now have two separate products, the product from k equals 1 to infinity of 1 over e times 1 minus 1 over 4k squared raised to the negative 4k squared power. And we have this other product, which is the product from k equals 1 to infinity of 1 minus 1 over 4k squared. And for this, we use the product representation of the sign, which says that sine of pi x over pi x equals product from k equals 1 to infinity of 1 minus k squared, or x squared over k squared. And then we just set x equals 1/2, and we get exactly this summation right here. And sorry, this is also a little bit iffy. This should actually say 1 minus 1 over 4k squared. And so this is our product. It's just equal to 2 over pi, which I think is really cool. And this is also the inverse of the Wallace product, which I know is very famous. So then we are going to have to deal with the rest of this here. So we're going to take our overall product P is 2 over pi times this product right here. And now what we're going to do is a nice trick when dealing with infinite products is we're going to take the natural log of both sides. And the reason we want to do this is because we want to get rid of this nasty power right here. And actually what it'll do is it'll turn our infinite summation into, or infinite product into an infinite summation. So what that's going to look like is we have ln p equals ln 2 over pi plus natural log of the infinite product. And now we use this fun little rule which says that natural log of a product of some factors ak is the same as the sum of the natural log of the factors, which of course just follows from ln ab equals ln a plus ln b. So we get that ln p equals ln 2 over pi plus the sum from k equals 1 to infinity of negative 1 minus 4k squared times natural log of 1 minus 1 over 4k squared. And we're just going to call this s. So this is our expression for s right here. And in order to solve s, well, these natural logs are not very fun to deal with. And one thing we could try doing is actually expanding this natural log out as an infinite series, but then what's going to happen is we're actually going to end up with some zeta functions, which is not too fun to deal with. Usually we actually want to move the other way around when we're talking about zeta functions. So what we're going to do instead is we're going to parameterize. So this is sort of similar to Feynman's trick when it comes to integrals, except we're doing this with a summation. So we're going to set s of x equal to the sum from k equals 1 to infinity of negative x squared minus 4k squared natural log of 1 minus x squared over 4k squared. And the reason we're putting these x squared in two places, well, first of all, the x squared inside the natural log means that when I differentiate with respect to x, the natural log disappears and it becomes a rational function. And the reason I have the x squared over here is because if I just left it with the natural log here, then I would actually end up, this term would just get differentiated away, and we would end up with the sum from k equals 1 to infinity of 4k squared over 4k squared minus x squared, and it's easy to see that this just diverges. So in order for it to converge, we need to actually keep this minus 1 term over here. So that's why we put x squared right here. Another way to think about this is if you expand natural log of 1 minus x as a power series, then you'll see that the first term of expanding this as a power series is just going to be x squared. So we also have to subtract this x squared in order to cancel that out, because the limit as k goes to infinity of x squared is just x squared, and we want the summation to converge. So we differentiate, we bring the 2x to the outside, and we get negative 1 plus 4k squared over 4k squared minus x squared. Then we go ahead and put this all over a common denominator, and we get x squared times the sum from k equals 1 to infinity of 2x over 4k squared minus x squared. Partial fractions right here. Very, very straightforward. And then we're actually going to shift the index. And the reason we shift the index is because we want this to be a sum from k equals 0 to infinity, because it allows us to apply the digamma function. So we shift the index, which makes this 2k plus 2 minus x and 2k plus 2 plus x. And then we divide by 2 on the top and bottom. So we get x squared over 2 times the sum from k equals 0 to infinity of 1 over k plus 1 minus x over 2 minus 1 over k plus 1 plus x over 2. So overall, we get negative x squared over 2. Digamma of 1 minus x over 2 minus digamma of 1 plus x over 2. And if you're wondering how this turns into that, just go ahead and plug in these two with the definition of the digamma function as a summation, and you'll see why this works. Next, we're going to use the digamma function recurrence relation, which says that digamma of 1 plus x is the same as, or 1 plus y, I should say, is the same as 1 over y plus digamma of y. So in this case, y is negative x over 2. So we subtract 2 over x, and we have this right here. And then we use the fact that digamma of 1 minus z minus digamma of z is pi cotangent of pi z. So in this case, z is just x over 2. Actually, z is negative x over 2. And so we have to bring a negative sign out here. So we get s prime of x equals x minus x squared over 2 pi cotangent of pi x over 2. Now, in order to see how we're going to use this s prime of x, we first need to know what values of s of x we know. And immediately, we notice that s of 0 equals 0, just going back into the definition, because the entire summand will be 0 everywhere. And s of 1 was just our original summation s. So that means if we integrate from 0 to 1 s prime of x, it's going to give us s of 1 minus s of 0. So that's just s minus 0, or s. So that's what we're looking for. So now we just have to integrate this function from 0 to 1. And that's relatively straightforward. This first term just becomes 1/2, and then we subtract the integral from 0 to 1 of x squared over 2 times pi times cotangent pi x over 2 dx. Then we substitute x equals 2u over pi, and we get this right here, and now everything looks pretty nice. We have u squared cotangent of u du, and we're integrating from 0 to pi over 2. Now, in order to get this cotangent of u into a nicer form, and to reduce the power of the u here, we're going to integrate once using integration by parts. And we get u squared natural log of sine of u, evaluated at pi over 2 and 0, which just goes to 0, plus 8 over pi squared, integral from 0 to pi over 2, u ln sine of u du. And this integral right here is a very, very fun one. It's one that I made a previous video on, so I'm just going to substitute in the value that we derived in that video. But I'll go ahead and put a card in the corner for you guys if you want to check out the proof for this nice integral. If you don't want to check out the proof and you want to try it yourself, just go ahead and use complex numbers in general. So it's 7 over 16 zeta of 3 minus pi squared over 8 times ln 2. So that means overall our summation s equals 1/2 plus 7 over 2 pi squared zeta of 3 minus ln 2, which means that ln p equals ln 2 over pi plus 1/2 plus 7 over pi squared zeta of 3 minus natural log of 2. And overall everything is going, our p is going to be e to the 7 over pi squared zeta of 3 plus 1/2 in the exponent and all over pi. What a magnificent result right there. I really like this infinite product just because it allows us to use a lot of different strategies at once. I mean, first of all, we use the infinite product for sine x over x, which is always fun. And then we used sort of analog to Feynman integration for summation. And so yeah, so I hope you guys enjoyed this video. If you want to see more content like this, please go ahead and leave a like or leave a comment of whatever problems you want to see. And if you want to join my Discord, the link's down in the description, and you can suggest problems there as well. So thank you so much for watching, and I'll see you next time.